Hello and welcome. In this video today I'd like to demonstrate the behavior of magnetic fields in a transformer arrangement related to the high power motionless generator by claimant Figuera. Initiated was my renewed interest in coil design and transformer and motor technologies by the announcement of Holcomb Energy System, which brings to market a successful tested product. It is called the HES solid state generator. It is a non-rotational motor design. You see a picture here. The idea is, as seen by many, to work in their design in this fashion that the individual windings or groups of windings are switched on and off in sequence so that the frequency of the output reaches either 50 or 60 Hz. At this frequency, we could use household consumers if the voltage is achieved for the respected frequency. In my test setup today, I look at the wave propagation of different setting scenarios. I use one module from the claimant Figuera setup. Let's have a look at the demonstration table. The primaries are connected in parallel in my first setup, in the same way a motor coil would be connected. I use two oscilloscopes to measure the waves. The left one on the screen measures the wave to the primary and the right one on the bottom measures the wave coming out from the secondary. Power input is displayed on the top on the left hand corner. Just to recap briefly what I just said before. So we have both primaries connected in parallel. That means both are connected in parallel, and the secondary output is currently not connected. That means we have an open line of the primary. So we're going to see then the wave behavior of getting power in and getting power out, and we would see how that looks like. So in our first test we have the secondary open and we have the primary connected here in parallel, and we have a classical 90-degree lacking of current for a transformer, as you can see on the right hand side. On the left hand side we see the pulses coming in, and we have also a lacking of current, and there is actually almost nothing coming in. So we have here 5 milliampere. Now that's actually showing exactly how it is. I see on the left hand side the green curve shows 5 milliampere, and that's exactly how much we are putting into the system from the DC power supply as well. There's not much more to say here at that one, because in order to have some more performance we need to change the wiring on the transformer. We have to cross that wire, and that will have right away an impact. So I will go over now to the next configuration with a crossover connection. Now after the turning off the wires, you can see here, and I have also added a little gap now here. You can see that the gap is making a big difference. We're going to talk about that a little bit later. But changing the wire in this direction is making a big difference. Need to adjust that gap again. Get a highest output. So what we can see here, we have 100% reactive power, and reactive power is a very important factor which needs to get delivered from a transformer to the load. But this power needs to be converted by your load to real power, and if you have loads connected like motors or additional transformers, they will lead to a leading or to a lacking current. Means that power factor will not be 1. That means you consume much more power from your power company, which will fine you for that if you don't take care of taking care of your power factor, which can be done by adding a capacitance to the inductor to shift then the phase back to the phase of the voltage, that we are coming back to close to 1. That means to our perfect way of transmitting energy to our load or consumer. So we can do that by adding a capacitance. So I will do that now to demonstrate how our wave will look like when we add capacitance to the system. I have now added a small capacitor. That is of course currently not 100% tuned capacitor, but as you can see at the waveform, first of all we are dropping in the frequency dramatically, and as you can see here we have a much better performance on the output side. It is not 100% in the center. That means we are still a couple of percent off, but it's much better, and you can see that on the power output it looks as well like that, but it's still circulating power. It's currently not power we can use. We would have to require now add an additional load here and compensate. That would also then have an impact on the frequency. So all this kind of changes and requirements, they are not really in that importance if we are out of resonance. So if we are working at 50 or 60 hertz, and at 50 or 60 hertz we are definitely not in resonance, and there are only the pulses there which work, and we have different ways to compensate for that. So also say we can use a capacitor, and a main system, definitely there are capacitor systems existing which take care of this problem of getting the power factor up. So if I move now coils here a bit, you can see I can influence that. So we can change technically with the gap the power requirement. That means I can get much more out. As you can see here, I come over 30 watt, if that is visible here, because of the changes I made here. And you see on the input side as well, we have a much better curve. We can see here, but it looks like here that our leading or lacking current becomes a leading current. So that's quite interesting to see here. So we measure here from a current point of view, we measure 28 milliampere RMS, and we have 22 milliampere here on a power supply DC. So we have still the circulating energy. Voltage is 15.7, 15.8 volt on the input side. We have 5 volt in here. And interesting is from the Figuera setup is that the primaries are much larger than the secondary. So if you see on the picture, you see that the primaries are much bigger than the secondary. Well, you need to multiply now that with many modules here behind connected, and then that will add here. We will have two phenomena. First of all, here we have series resistance on this coil. That means our impedance will increase, and here we have parallel connections. Here our impedance will decrease. That means we will have much more current coming out here on that side, and we are consuming less current on this side. So this is a quick overview of the system here, what to look out for. I know a lot of people, a lot of you are investigating with that subject, work on that and have a look. And there's definitely something in there which is worth further investigating. Thank you.